electrons were once thought to orbit the nucleus like planets around the Sun. And that picture was blurred by modern quantum mechanics. An atom is best visualized as a tight, dense nucleus surrounded by fuzzy electron clouds. This picture immediately leads to a question. How do electrons keep orbiting the nucleus without ever falling in? This was a nagging question in the early 20th century, and the search for answers ultimately led to the development of quantum mechanics. Quantum mechanics is a fundamental theory in physics that describes the physical properties of nature at the atomic and subatomic level. Classical physics, describing physics before relativity and classical mechanics, describes many aspects of nature in the ordinary, macroscopic level, while quantum mechanics explains aspects of nature at the microscopic level, including molecules, atoms, and smaller than atoms, where classical mechanics no longer accurately describes. Quantum mechanics differs from classical mechanics in that energy, momentum, angular momentum, and other quantities of a balanced system take discrete or quantized values. Entities exhibit both particle and wave characteristics, also known as wave-particle duality, and there are limits to calculating the precision of physical quantities before each measurement, given by a complete set of initial conditions, also known as the uncertainty principle. In the early 20th century, after numerous experiments, physicists began to piece together a unified picture of the atom. They realized that each atom has an S, heavy, positively charged nucleus surrounded by a cloud of small, negatively charged electrons. With this rough picture, their next step was to create a more detailed model. In their first attempts at modeling this, scientists drew inspiration from the solar system. The solar system has a dense nucleus as the Sun, surrounded by a cloud of smaller particles as planets. But this model presented two significant problems. The first problem: an accelerating charged particle emits electromagnetic radiation, and because electrons are charged particles and they accelerate in their orbits, they would emit radiation. According to the University of Tennessee at Knoxville, this emission would cause electrons to lose energy and quickly spiral inward and collide with the nucleus. In the early 1900s, physicists estimated that such an inward spiral would take less than a trillionth of a second, or a picosecond. Since atoms clearly live longer than a picosecond, this wouldn't work. The second problem, more subtle, relates to the nature of radiation. Scientists already knew that atoms emit radiation, but they do so at specific, very distinct frequencies. Instead, an electron orbiting in this solar system model would emit all kinds of radiation, contrary to observations. The famous Danish physicist Niels Bohr was the first to propose a solution to this problem. In 1913, he proposed that electrons in atoms cannot have any orbit they want. Instead, they must be confined to orbits at very specific distances from the nucleus, according to a long citation for his subsequent Nobel. Additionally, he proposed that there is a minimum distance that an electron can reach and it cannot move closer to the nucleus. He didn't just pull these ideas out of a hat. More than a decade earlier, German physicist Max Planck had proposed that radiation emission could be quantized, meaning an object can only absorb or emit radiation in discrete chunks and not at any value at once. But the smallest size of these discrete chunks is a constant, called Planck's constant. Previously, scientists thought such emission was continuous, meaning particles could radiate at any frequency. Planck's constant has the same units as angular momentum, or the momentum of an object moving in a circle. So, Bohr applied this idea to electrons orbiting the nucleus, saying that the smallest possible orbit of an electron would have an angular momentum of exactly 1 Planck's constant. Higher orbits could have twice that value, or 3 times, or any other integer multiple of Planck's constant, but never any fraction like 1.3 or 2.6, etc. The full development of quantum mechanics was needed to understand why electrons have such a minimum orbit, and higher orbits are clearly defined. Electrons, like all matter particles, behave as both particles and waves. While we can imagine an electron as a tiny planet orbiting the nucleus, we can also easily visualize it as a wave wrapped around that nucleus. Waves in a confined space must follow special rules. They can't just have any wavelength. They must be made from standing waves that fit inside the space. It's similar to when someone plays a musical instrument. For example, if you pin both ends of a guitar string, only certain wavelengths will fit and give you distinct notes. Similarly, the electron wave around the nucleus must fit, and the closest orbit of an electron to the nucleus is given by the first wave of that. Future developments in quantum mechanics will continue to refine this picture, but the fundamental point remains. That an electron cannot get any closer to the nucleus because its quantum mechanical nature won't allow it to occupy less space. That's a completely different way to consider the situation that doesn't. An electron orbiting the nucleus is electrically attracted to the nucleus, is always being pulled closer, but the electron also has kinetic energy, which tends to push the electron away. For a stable atom, these two balance. In fact, the total energy of an electron in orbit, the sum of its kinetic and potential energy, is. That means you have to add energy to the atom if you want to remove the electron. It's the same situation with planets in orbit around the Sun. To remove a planet from the solar system, you have to add energy to the system. One way to view this situation is to imagine an electron falling toward the nucleus attracted by its opposite charge. But because of the rules of quantum mechanics, it cannot reach the nucleus, so it gets stuck and orbits forever. But this scenario is allowed by physics because the total energy of the system being negative means it's stable and bound together, forming a long-lasting atom. Thank you for your attention. If you found this video interesting, don't forget to like and subscribe to watch more videos at hidden_realms. Hello and see you again next time. Subscribe to the Gian Migo channel so you don't miss out on exciting videos.